Hello students, today I am going to demonstrate a case study on random effect additive model that developed in statistical software R. To do this, I am going to take a data. Data is about skin color measurements of 7 participants over 3 weeks. So, initially I will explore the data to understand the different assumptions that is required for fitting the model. So, descriptive analysis is one of the compulsory part for any such model fit. So, I will start with the descriptive analysis and then I will fit a mixed effect model where, as I mentioned, two factors here. One is the weak and another is the participants. So, in the first part I will consider participant as the random effect and weak as the fixed effect, and I will fit a fixed effects model, that is one random and one fixed, and then I will seeing the data and try to show you how to interpret the result. And then as a second step, I am going to consider both the factors, one weak and the participants are random. So, fully random effects model would be fitted, and alternatively I will show different other functions that can be used to fit this model in R. And finally, as a part of the pair comparison, I will show you how to do the postdoc analysis here as a multiple test exercise in R in the case of mixed effects model. And I am expecting after completion of this module, students should be able to understand how to analyze the data, especially for mixed effects model and random effects model in R, and how to conclude about the different variance components that is going to be extracted in my exercise. So, that and testing for those variance components, and then finally arrive at the final model. That is the main objectives that the module has. To understand the context of random effects additive model, we really need to understand the data very clearly. So, I will focus a little bit time on understanding the data. Here the following data is from a study of skin color measurements among 7 participants named as A to Z, A, B, C, D, E, F, G over the 3 weeks. In this study, not only is there variation among the participants, but there is also variation for each participants over 3 weeks of study. Experiments that are intended to study factor effects on skin color, that is shortened products and skin color, must be designed so that the variation in subjects and across time does not mask the effects of experimental factors. And here is the data. So, there are 7 participants and weekly skin measure 3 weeks. Over 3 weeks the skin measurements are here in 3 columns. The measurements in the table were taken on 7 participants during each of 3 weeks of the study. Note that it is not the specific participants who are of interest to manufacturer of skincare product, but the population of possible purchaser of this product. That means those 7 participants were selected randomly. We first assume weak effect as a fixed, but participant as the normal random variable. The standard deviation of the distribution measures the variability in measurements that is attributable to different skin types among intended purchasers. Second, we assume both participants and weak effects are random effect, because environmental conditions and other influences such as daily hygiene and exposure to sun, etc., that can affect skin color measurements are not controllable. Each individual does not have the same skin color measurements each week of the study. the standard deviation of each assumed normal distribution measures the contribution of week to week variation to the overall variability of the skin color measurements. One can also consider the conclusion of random interaction effect between participants and weeks of study, but I am not going to focus here. So, data can be entered in this manner. The data was in tabular form. So, I create 3 variable week 1, week 2 and week 3, and then 3 can be and participant variable participant can be created by these comments, the letters sequence from 1 to 7, then it will automatically create the letter sequence A to G, and then form a data frame, form the data with the use of the function data dot frame, the skin color, then week and the participant, and altogether it will give the data. If you want to see the data, just type data, that will give you the data that you have entered and formed as a data dot frame. So, there are 3 columns, as you can see, the skin color and then week and then participants. So, before I feed the mixed random effect and mixed effect model, I just have a look on the distribution of the data. To see the distribution of the data, best way to visually get the distribution is the box plot that gives lot of informations from the plot. If you just see this data, for weekly variation, if you see that there is very mild variation, it may not be significant, whereas the interpersonal variability is quite high. So, that means participant to participant variations very high. Maybe this part would be significant, but this may not be significant. So, let's have a look in the test, then we can conclude it. But I am going to show you different alternatives, because there is not a single functions exist in R to perform this particular test. So, there will be several, out of which few I am going to show you first. So, first I will start with the ANOVA with random intercept. In random intercept is the participants, and the weekly effects is considered to be the fixed effect, and you just use the function AOV, that is skin color, then 2 factors week and error, and within this error function you should pass the participant given week, then this would be considered as the random effect, the random intercept, and data equals to data, that will fit and generate a ANOVA object. And if you get the summary of the object feed, it will give you the summary. Here is the actually fixed effects ANOVA, which is indicating its not significance, and as its not significance, we should stop here. But for our understanding, and to learn, if it was significant, what would have been the next steps as a pair comparisons. And though it's not significant, but I'll show you how to do the pair comparison in the context of random effect model or mixed effect model. So, alternatively, I use the library NLME, where in this library there is a function called LME, that is linear mixed effects model. That function can be used in this fashion, that skin color, then week, and then comma random equals to, that will assign 1 given participants by week, and data equals data. If in this form you need to enter the pass by values and then get the summary, and the summary will be generated in this fashion. There would be the random component, that is the variance component values, and here would be the beta, the fixed effects beta that would be available. And in just if you might be interested about the ANOVA table, so just within ANOVA function you pass that LME objects fit, that will generate the ANOVA table. Here also it is indicating that the weak effects are not significantly different. So, but we should stop here, but at a just to show you how to do the multiple testings, I'm just showing here, but in this, remember, in this again I am telling, in this examples you are not supposed to perform any multiple comparison or the pairwise test, because it is not significant. The multiple comparison or ANOVA postdoc test only perform when the ANOVA is significant, but just for your knowledge I am showing how it's need to be done, but the results would be all insignificant. So, here the library multicom, one library exists as a multicom. If it's not there, you can download and install. That library multicom is responsible for all type of multiple comparisons, and here the GLHT is one function is there where you pass that LME object, and then LINFCT equals to MCP. MCP means multiple comparison is weak equals to 2 key. So, weak is the fixed factor. So, fixed factor equals to 2 key, where the fixed factor pairwise comparison would be done, and that will generate the multiple comparison results. If you see week 2 versus week 1, the test was week 2 minus week 1 equals to 0, week 3 minus week 1 equals to 0, week 3 minus week 2 equals to 0, the mean actually. So, these are the hypotheses, and these hypotheses, the estimates are given, the standard error given, the z values are given, and then finally the p values are given. This estimate means it's the difference between W2 and W1, the skin color measurement difference between week 2 and week 1, week 3 and week 1, week 3 and week 2. These are the estimates and their standard deviation and their corresponding p value. As I mentioned, as ANOVA itself insignificant, so definitely the multiple comparisons show you the insignificant results. So, hope you'll be able to apply the 2K HSG test in the context of a mixed effects model. So, now as I mentioned in a second step, I am going to consider the weak also as the random effect. So, 2 random effects instead of mixed effect, I can fit the random effect model. So, consider both weak and participant effects are random. To do this, we can use the same manner, the first syntax that I used for AOV function, the skin, and then within error function you put participant plus weak, then these two would be considered as the random components. And to get the summary, you can just generate the summary from this object, and it will give you the 3 components, the 3 of the variance components. That is, first one is the variance component related to the participant, degrees of freedom 6, sum of square this, mean is this and this, and the next variance, next ANOVA component, this residual error is related to the weak, that variance component related information, the ANOVA table. And then within one, that is the residual error, the random error, that related ANOVA table would be given. You can calculate the AF value, but the function won't give you the AF value. So, you can calculate the AF value very simple, this by the error one. Where is that? This one. So, this value divided by this value, you will get the F value, and from F value you can calculate the P value. So, P value can be calculated as PF 180 is the value, and 6, 12 is the degrees of freedom, and lower dot tail equals to false, then it will give you the P value, and finally 186, sorry, it will be 186, mistakenly I put the 80. And then similarly you can calculate the p value for all the cases. So, again you see that weak random effect, if weak as a factor is not significant. So, the skin color doesn't vary across different week of measurements in this data set. So it is not significant, whereas the participants are statistically significant. Alternatively, I can use the same for LME4 functions, that is LMER. This is another one. So last time I have shown you the NLME. Similarly, the mixed effect can be fit by LME4 package. The function is LMER, and this LMER function, it is the syntax is little bit different here. The skin color, and then within bracket you pass one given participant plus one given week, and then pass the data equals to data if data is not attached, and that will generate a linear mixed effects model objects. If you need the summary, you can just get the summary of this, and that will give you the summary as a linear regression, linear mixed effects model. It would be some fixed effects component would be there, and the random effects components are there. These are the variance component of all related to, I mean, three variance components. One is the participant, another is the week, another is the residual, that is the random error. These are the 10.2.5 is the participant variance component, whereas week variance component is almost 0. So it's up to 3 decimal, it is 0. That means the week is not at all a random component. It can be considered as a fixed effects rather than random effect, as the variance component is 0 itself. It doesn't need the testing at all, because estimate itself is near to 0. So we can modify the model, and we can retain the same earlier model where the participant as a random and week as fixed, and that would be your final model. So if you just want to see the actual testing procedure, here the most convenient way to test those hypotheses for the variance components is the calculate the 95% confidence interval. If the 95% confidence, as you know, that if the 95% confidence interval does not include the null hypothesis value, where the hypothesis was sigma 1 equals to 0, sigma 2 equals to 0, and sigma 3 equals to 0. So that means if the 95% confidence interval does not include 0, then they would be significant, and if it includes 0, it is not significant. So let's see, it is based on the profile likelihood methods. It will compute the 95% confidence interval, but you can change it. You just get the help of Marmot function, and see there will be a lot of alternative way to compute the 95% confidence interval. So here by default it's doing the profile confidence interval profile likelihood method, but you can do a bootstrap method, which is the most popular one, where in the bootstrap method you may have to mention the number of samples that is required, and these three random components, sigma 1, sigma 2, and sigma is the random one. So if you see that sigma 2 is 0 to 1.76, that means it includes 0. So sigma 2 corresponding to the weak effect. So weak effect was not random at all. So as sigma is 0, so it is degenerated. So it's not normally distributed. It's just a constant, and so that can be considered as a fixed effect, whereas sigma 1, that is the corresponding to the participant, it is actually random, and they are statistically, and it is statistically significant. So that can be considered as a random effect. So it's a mixed effects model. Actually the final model will be the mixed effects model, where participants should be considered as the random component, and the we could be considered as the fixed effect. And so the final model then would be derived as the skin week plus error participant per week, and data equals to data. That will give you the summary of the final results that you must have seen early, initial slides. And as you saw that weekly variations is not significant. Only variation that we observe here is intrapersonal, intra-individual variability, that is person to person, the skin color. The effect of skin color varies across participants, but not across the different week of measurements. So I think these are the few different alternatives way of fitting random effects model and mixed effects model and their related multiple comparisons. There are a lot of other alternatives are there, if somebody wants can explore. As a summary, in this module we have learned the different functions that use to analyze the linear mixed model or linear random effects model, and also I have shown how to extract the variance components and test the hypothesis, and also along with that what are the different descriptive analysis that is required prior to the linear linear mixed effects model or random effects model fit, that also shown in this module. So as a whole what we learn is that to analyze the random effect or mixed effects model, especially the LME or LME4 from the NLME function package and another from the LME4 package that mostly we used, and if for the mixed effects model that we also have learned how to do the multiple testings for the pairwise comparison.